In our last few examples, we have computed path integrals by finding potential functions for vector fields and using the fundamental theorem of line integrals. And it's kind of been like we hoped we could find that potential function. It turns out there's a test. This is called the component test for a conservative field. If we do this test first, then we know there is a potential function instead of just hoping there is one. Let F be a vector field with components m, n, and p. Let that be a vector field on an open, simply connected domain whose components have continuous partial derivatives. Okay, in our last video, we talked about the idea of connectedness, that if I have a region in space and I can connect any 2 points on the inside of it with a path also on the inside of it, we call it connected. And that gave us this idea that both regions here are connected. Well, it turns out this region is what we call simply connected because it has an additional property. It's connected, and any loop I draw on the inside of it can be shrunk to a point without getting caught up on anything. Every loop is contractible. Over here, if I try that, I draw a loop over here, well, I can contract that to a point by making it smaller and smaller. Imagine like pulling a string into a knot. But if I put a loop around the donut hole, I'd never be able to shrink it any past, well, this kind of inside equator, right? The innermost part of the donut hole. So this theorem only holds if I have a simply connected space. Well, this test has 3 parts. So I have a vector field m and p, and I compare the components. If I think about it, I'm comparing m and n, m and p, and then n and p, all 3 possibilities. And what I'm doing is comparing their partial derivatives. So the partial of m with respect to y has to be equal to the partial of n with respect to x. The partial of m with respect to z has to be equal to the partial of p with respect to x. And then finally, the partial of n with respect to z has to be equal to the partial of p with respect to y. The way I like to think about this is I write down partials for m and n, comparing m and p, comparing n and p. Right? All the ways I can pair up these 3 things. And then if I look at the partials, well, m is the x component, n is the y component, and it's like they're backwards, right? It's like I'm taking a different partial of it, and they all have to equal. We'll talk about why that is in a minute, but I thought we'd use the component test first. So here is a vector field that we actually used in our last example. We found a potential function for it. And we were kind of in that situation where we were just hoping to find the potential function for it, hoping that it was conservative. Well, I would say the smarter thing to do is to actually use the component test, because after I'm done with that, I'll either know whether there's a potential function or not. So I need to compare the partial of m to the partial of n. And that's a partial with respect to y and a partial with respect to x. So I'm going to go on and compute those 2 things. So the partial of m with respect to y, well, that's 0. The partial of n with respect to x is 0, and those are equal. So we've passed the first part of the component test. So now I'm going to think partial of m and p. So this is a partial with respect to z, and this is a partial with respect to x. The partial of m with respect to z, well, that's 0. And the partial of p with respect to x, well, that's also 0, and those are equal. We've passed the second part of the component test, 1 to go. And so I need to think about n and p. All right, so that's a partial of n with respect to z and a partial of p with respect to y. All right, the partial of n with respect to z, well, that's 2z over y. The partial of p with respect to y, well, that would be 2z times the derivative of the natural log of y, well, that's 1 over y. And those are equal, and so f must be conservative. Which means when we go through and try to find a potential function, we'll actually be able to do it. It has to exist. I'm not just hoping, and I'm not just going to try. And this way I know I will be successful if I go through all the details. All right, so what's making this work? Well, I'm not going to prove this theorem. I'm not going to prove the if and only if part. But I am going to show you the relationship between these partial derivatives. The idea being that I can show you that if f is conservative, then these statements hold. So I'm going to show you that if f is conservative, then these three things are true. To prove the other direction requires a statement known as Stokes Theorem. So the idea here is that if f is conservative, that would imply that f is a gradient field. And it has some potential function. And this is going to let me rethink what these actually say. Okay, so what this really is, well, m is the partial of that potential function with respect to x, n is the partial with respect to y, and p from the original statement was that partial with respect to z. So when I write the partial of m with respect to y, well, that's really a partial with respect to y of whatever m is, which is the partial with respect to y of the partial of f with respect to x. And so that statement itself is really a mixed second partial derivative. And this is the really cool part, if you ask me. One of my hypotheses was that my component functions were continuous and had continuous partial derivatives, which means Fubini's theorem applies. My mixed partials are equal. So the mixed partial of f with respect to x and then y is the same as the second mixed partial of f with respect to y and then x. And just kind of following the notation around, that would let me write this statement. Well, the partial of x with respect to this, well, that's n. And so the partial of n with respect to y has to be equal to the partial of n with respect to x. And so all this statement really is saying that, hey, check to see if the mixed partials are equal. And that'll show you that your field is conservative. The part I've actually proven here is that if f is conservative, then this statement is true. It takes a little more effort to prove it the other way.